Welcome to this explainer. Today, we're popping the hood on the modern world to look at something that, let's be honest, probably gave you a headache in high school, calculus. But we're going to shift it away from those dry textbook formulas and look at it as the fascinating, absolutely essential engine that quite literally drives our reality. Let's just dive right in, because the stakes here are absolutely monumental. To really get what calculus does, we got to compare it to what you probably already know. Think about geometry and algebra. They're great, right? But they give us static snapshots of the world, fixed shapes, strict equations. Calculus is a whole different beast. It's the math of motion and dynamic systems. It lets us zoom in and see exactly how things are changing at any precise, instantaneous moment. Section 1. The math of motion. So if we strip this tool right down to the studs, the definition is actually surprisingly simple. Calculus is just the mathematical study of continuous change. It's basically the underlying language that lets us make sense of highly dynamic, ever-shifting systems, rather than just looking at frozen moments in time.
And it brilliantly splits into two mirrored branches. Think of them as two sides of the same coin. First up, differential calculus. This is all about rates of change. It asks, how fast is this thing changing right now? And uses a tool called the derivative to pinpoint the exact slope of a curve at a single point. On the flip side, we have integral calculus. This one's all about accumulation. It asks how much total stuff has piled up over time by using the integral to calculate the exact area under a curve, basically stitching infinite tiny pieces into a single whole.
Section 2. A nonlinear world. Now, you might be wondering, why go through all this trouble, right? Why not just stick to basic math? Well, before calculus, math was kind of stuck measuring things that were perfectly straight or totally constant. Take basic algebra. If you're cruising at a constant 60 kilometers per hour, distance equals rate times time. Easy. But that's a static snapshot. In the real world, you accelerate onto the highway, you brake for traffic, you stop at a red light. Your speed is constantly fluctuating. Because our reality isn't a straight line, we absolutely need calculus for three core things. Number one, calculating instantaneous speed. That's literally what your speedometer shows you at any exact second. Number two, finding optimal points in a changing system. Think about finding the precise price point to maximize your business revenue. And number three, measuring totally irregular shapes that just completely defy standard formulas. Section 3, calculus in action. All right, let's take this into the real world. This math literally runs the show everywhere. In physics and engineering, you cannot design a safe bridge or map out a rocket's trajectory without it, because gravity and acceleration are always shifting. In finance, quantitative traders use it to model the wild, unpredictable swings of the stock market. Over in data science, AI learns to recognize patterns using a calculus process called gradient descent. Even in medicine, biologists rely on it to model exactly how a virus spreads or how a drug concentrates in your bloodstream over time. Section 4. A world without it. So yeah, that is a massive footprint. But to truly wrap your head around its importance, imagine this. When Isaac Newton and Gottfried Leibniz independently figured this stuff out in the 17th century, it was a total game changer. If they hadn't made that leap, the technological timeline of human history would have basically flatlined right then and there. We'd never have hit the milestones of the 20th and 21st centuries. We'd be looking at an absolute technological disaster. Space exploration? Gone. You can't launch a rocket if you can't calculate its changing mass as it burns fuel, which means zero satellites and no GPS. Our architecture would be totally primitive, either dangerously fragile or massively over-engineered because we couldn't calculate changing wind loads. Modern electronics wouldn't even exist, since the laws of electromagnetism, the stuff powering the device you're using right now, are written entirely in calculus. And medicine, it would be reduced to incredibly dangerous guesswork. So, in short, without calculus, our world would look structurally and technologically way closer to the 1600s than the 21st century. By swapping out guesswork for precise, dynamic mathematical modeling, this hidden engine is straight up the single biggest reason we get to live in the modern era. We've definitely covered a lot of ground in this explainer today, diving into how the math of continuous change literally built our modern reality. Now that you know the monumental stakes working behind the scenes of our daily lives, I'm going to leave you with this. Would you like to explore the core concepts of derivatives or integrals with some practical, real-world examples next? It's a fascinating journey, and I really hope this sparked your curiosity to look a little closer at the hidden gears running our world.